So YouTube homework number 3. A. Draw and label a free body diagram for each of the following cases. So at first there's a gravitational force pulling down the box. There's a normal force of the table exert on the force. There's also a pushing force initially, and there is a static friction force that prevents the box from moving. For number 2, there is still the normal force of the table, the gravitational force, but then the frictional force got replaced by a kinetic friction force that is less than the pushing force this way. And finally, there's only the normal force and the gravitational force. B. Rank the magnitude of all the horizontal forces for diagram for instance 1. So initially the box is at rest and there's no horizontal force. So when you give the box a quick push, you apply a horizontal force to the object and cause it to accelerate or move. So you can only accelerate the box when the pushing force that you apply is greater than the static friction force that keeps the box from moving. So basically I got that the pushing force is greater than the static friction force. So C, are any of the forces that you drew for instant 1 missing from instant 2? So basically I said that the static friction force is missing from diagram 2 and got replaced by the kinetic friction force. So the static friction that used to keep the object stationary turned into kinetic friction that causes the object to slow down. So I knew that the static friction force on the first instant, because at first it was static, the force wasn't moving at first until you apply a quick push that exceeds the frictional force. Are any of the forces that you drew for instant 1 missing for your diagram for instant 3? So for instant 3, since the box is at rest, which means that the net force for the horizontal component is equal to 0, and I got that the applying pushing force is missing and also the friction force. Since there's no push or pull on instant 3, you didn't apply any horizontal force on the object, and the static friction force isn't included because by Newton's third law of motion, forces only come in pair in opposite and equal magnitude. Since there isn't a pushing force this way, there's no need to include a static force to counteract that, and it shouldn't be included in the context of the problem. So, how does the acceleration of prey A compare to that of prey B? So the acceleration of the two prey are equal to 0 because the elevator is moving with constant velocity, which means that the acceleration is equal to 0. And since the two blocks must be traveling with constant velocity as well because they're in the elevator. For part B, draw the separate free body diagram. So for prey A, there is a gravitational force pulling down, and there is also a normal force that block B is pushing up. For prey B, there is a normal force of the floor pushing up, and there is a normal force of prey A pushing down. So rank the forces on the prey according to magnitude from largest to smallest. So as you can see here, the normal force of prey B is equal to the gravitational force, which is larger than the normal force of prey A and equal to the normal force of prey of the floor. So based on the equation F is equal to ma, we can see that 0 acceleration means 0 net force. However, the individual forces on prey A is still bigger than prey B due to its greater mass. And by Newton's third law, there is also an opposite and equal magnitude to the applying force. So in this case, the counteract force to the natural force B is gravity, and the counteract force to the natural force A is the floor. So these two are equal, but since Cray A has a bigger mass, then the force on Cray A is also bigger. In the space it provided at the right, draw an arrow to indicate the direction of the mass force on each of the Cray. So I got that the net force for Cray A and Cray B equal to 0. So by Newton's second law, F equal ma, since there is no acceleration for the two boxes, therefore the net force have to be 0 on both Cray. And once again, the magnitude of the net force on A is equal to B, which is 0. So again, using Newton's second law of motion, we can see that 0 acceleration meaning 0 net force. So since they both have 0 acceleration, they would have no net force. Part B, as the elevator approaches its destination, speed decreases and continue to move downward. So how does the acceleration of Cray A compare to that of Cray B? So as you can see, I drew a motion diagram, and the velocity is going down while the acceleration is going up, which means the elevator is slowing down. So I got that the acceleration of the Cray are equal to one another, since they're in the same elevator, and we treat the system as a whole with similar acceleration. For part 2, draw a free body diagram for the Cray. So once again, you can see that there is a normal force of B counteract with the gravity force, but in this case, there is also a tension force of the cable that is trying to pull the elevator while it's going up, while it's going down, just to decelerate the elevator and make it slow down. Similarly, for Cray A, there is a natural force A pulling down, and there is a natural force of the floor pushing up, and there is also a tension force. Rank the forces on the Cray according to magnitude. So basically, I got that the normal force B is equal to the gravitational force, which is larger than the natural force of the floor, equal to the natural force A. But in this case, I added a tension force. So using the equation F equal ma, we can see that greater mass equal to greater force, so just like the previous case. So since the boxes accelerate upward, which means that the bottom force pushing up have to be greater than the force pushing down. And since Cray A is bigger, its force have to be greater as well. So for Newton's third law of motion, which states that forces come in equal and opposite pair, so you can see that these two are equal, these two are equal. However, in this case, the box is accelerating upward, which means there has to be another force. So there is your tension force right here. This force helps to pull the cable and slow down the elevator to a stop. Okay, part 4. Draw the direction of the net force. So I got that the direction is pointing up, but Cray A has a greater magnitude than Cray B. So the net force of the crate has to be positive because they're accelerating upward, assuming that we're using pointing up as y and then to the right as x, standard ASCII system. So as the magnitude of the net force on crate A is greater, less than, or equal to crate B. So again, based on the equation F equal ma, we can see that the two crate have the same acceleration, but different masses. Therefore, the forces have to be different. Since crate A has a bigger mass, which would result in a bigger force than crate B. So yeah, as you can see here, similar to the previous.